Hello guys, in this tutorial I will solve a problem where we are given three layers of insulation. As you can see in the given figure, we have layer 1 with permittivity epsilon 1 and we have layer 2 with permittivity epsilon 2, and in between we have air with permittivity epsilon naught, and the voltage applied between or across the insulation is shown here, which is 100 volt, which means voltage rises from right to left. So we have ground potential on the right side of the insulation, and we have 100 volt on the left side of the insulation. And the width of each layer is defined as 1 millimeter, and the cross sectional area of each insulation layer is, or the face area of each insulation layer is 0.2 dm square. So this is what we are given in this problem. Now we have to determine electric fields in each layer, but for that we need to determine permittivities in each layer as well. Okay, so let's start. So in the given condition, we have E1 ratio E naught ratio E2 equal to 2 ratio 8 ratio 3. Now, in this typical problem, as we can see, the voltage rises from right to left, and this applied voltage, which is 100 volt, is being dropped across different layers of insulation. So this type of um, combination of insulation layer is considered as a series combination of insulations. So in series combination of insulation, where we have um, applied voltage like this shown, then electric field distribution will be like this. Electric field will be from high potential to the low potential. Okay, so as we can see, electric field is perpendicular, so electric flux lines or electric flux density will also be perpendicular to the surface of the insulation layers. So if we have perpendicular electric fields on the surface of the insulation layers, um, then in that case we have electric flux densities in each layer of insulations will be equal. So D1 will be equal to D2, that will be equal to D3. Further, we can say that D1 is equal to epsilon 1 E1, and this is equal to epsilon 2, and we have epsilon naught. Second layer is air, so epsilon naught E naught, and this is equal to epsilon 2 E2. Okay, so then we can, from the first two terms of this equality, we can say that E1 over E naught will be equal to epsilon naught over epsilon 1. And this can further be written as, epsilon naught can be written as relative permittivity of air is 1. So we can write epsilon r for the air multiplied by epsilon naught. So epsilon r for the air is 1 multiplied by epsilon naught divided by relative permittivity for medium 1. So we have epsilon r1 multiplied by epsilon naught. Okay, so epsilon naught will be cancelled with epsilon naught. So we will be left with 1 over epsilon r1. And from the given ratio, we can see that if we take a ratio of E1 over E naught, so that will be equal to 2 over 8. Okay, so that is equal to E1 over E naught, that is equal to, from the given ratio, 2 over 8, which is equal to 1 over 4. Hence, epsilon r1 equal to 4. So we determine the relative permittivity of material 1, of insulation 1. Okay. Similarly, if we take the other half of the equality, okay, then we can write that E2 over E naught will be equal to epsilon naught over epsilon 1. And this can further be written as epsilon 2. So this can further be written as 1 multiplied by epsilon naught divided by epsilon r2 dot epsilon naught. And epsilon naught will be cancelled with epsilon naught. So this can be written as 1 over epsilon r2. And here from the given condition, from the given ratio, epsilon E2 over E naught will be equal to 3 over 8. Okay, so that is equal to 3 over 8. Therefore, epsilon R2 will be equal to 8 over 3. So we found the relative permittivity of material 1 and material 2. If we want to find the absolute permittivities of these materials, we can easily multiply these relative permittivities with the permittivity of free space. Okay. Now, next step is to determine the electric fields in each of these insulation layers. For that, we will take the voltage and electric field relationship across the whole insulation, which is U is equal to E1 D1 plus. So the voltage across the insulation 1 will be equal to electric field across this insulation multiplied by the thickness of this insulation. Similarly, voltage in the voltage across the air will be equal to electric field multiplied by the thickness of the air. So, or we can write it as U is equal to U1 plus U0 plus U2. And then further we can elaborate it as E1 D1 plus E0 E0 plus E2 D2. Okay. Now we have, in this equation, we have three variables, E1, E0, and E2. So we are going to reduce these variables to 1. How can we reduce these variables? Again, we can reduce these variables from the given conditions, from the given ratio. And from the given ratio, as given ratio is E1 ratio E0 ratio E2 is equal to 2 ratio 8 ratio 3. So from the given ratio, we can write the relationship between E1 and E0 as E0 over E1 is equal to E0 ratio E1 will be equal to 8 ratio 2. Okay, this is equal to 4, which gives us E0 equal to 4 times E1. Okay. Similarly, if we take a ratio between E2 and E1, we'll get E2 over E1 equal to 3 ratio 2. It gives us E2 equal to 1.5 times E1. Okay. So now we can insert all these variables in the first equation. So U will be equal to now E1 D1 plus value of E0 is 4 times E1. So 4 times E1 into D0 and plus value of E2 is 1.5 times E1 and D2. So now we have only one unknown, which is E1. Voltage is given, which is 100 volt. Thickness of each layer of insulations D1, D0, and D2 are also given, which are 1 millimeter. So we can determine the value of E1 equal to 15.4 kilovolt per meter. So once we found the value of E1, we can find the value of E0. So E0 will be equal to 4 times of E1. So E0 will be equal to 15.4 multiplied by 4. That will be 61.5 kilovolt per meter. And the value of E2 is equal to 1.5 times E1. So E2 is equal to 1.5 times 15.4. That will be 23.1 kilovolt per meter. So this is all. Thank you.